So now we know the mean of the error vector, we know the variance of the error vector, and we can think about the impact of the serial correlation on our least squares estimator. I was debating whether or not I was going to go back and look at heteroscedasticity for a minute, but I'll save it for another day. So let's talk about the consequences of autocorrelation for OLS. Our garden variety least squares estimator is still x transpose x inverse x transpose y. And we're interested in the expected value of that under this circumstance. So we use our usual procedure, substitute away from y. Take expectations. We already know that the expected value of the error vector is still 0, even though it's serially correlated. And so under the assumption of serial correlation, the garden variety least squares estimator is still unbiased. Let's take a look at the variance of our least squares estimator. So by definition, the variance of the least squares estimator is the expected value of beta hat minus beta, the quantity, times beta hat minus beta transpose. Substitute away, the same way we've done previously. Substitute away from the difference, beta hat minus beta, and we end up with x transpose x inverse, x transpose times the expected value of UU transpose times x transpose x inverse. Now we know, having just derived it, we know the expected value of UU transpose is that very special patterned matrix. So previously, when we had an error covariance matrix that was scalar diagonal, we had an identity matrix in here. And so the x transpose x canceled against one of the x transpose x inverses, and we got sigma squared x transpose x inverse. But now, because of this patterned matrix, that doesn't work anymore. So clearly, least squares is not going to be efficient. Because this is the coefficient covariance matrix when there is serial correlation and we apply OLS. We had the same phenomenon in heteroscedasticity. When you estimated your share equation by OLS, suppose for the moment that you did it my way, not yours, you estimated one of the share equations by OLS, and you knew that there was heteroscedasticity, but the computer didn't. Did it compute this kind of coefficient covariance matrix, or did it compute something else if you didn't tell it that there was heteroscedasticity present? Your computer software is always programmed the same way. There are certain default calculations. The default calculation for the coefficient estimates is x transpose x inverse x transpose y. It's always done that way unless you tell it to do something different. The default calculation for the coefficient covariance matrix is always sigma hat squared times x transpose x inverse. Always, unless you specifically tell it something different. If you have data, time series data, probably the error term is serially correlated. If you apply ordinary least squares anyway, with no serial correlation correction, your computer software is going to tell you that the coefficient covariance matrix is sigma squared times x transpose x inverse. Now we know that's not correct. The computer still doesn't know it, but we know it. We know that when we apply these squares in that environment, this was the coefficient covariance matrix. So the question is, how do we inform the computer that there is serial correlation? So we'll come to that in a minute, because we don't want to be misled by what the computer is telling us because we didn't tell it to do the right thing.